Okay, there we go. All right, so today we're going to talk a little bit about sort of our next set of stuff. So we started talking about op amps. So all last week we covered op amps. You guys can go back and review. We did a number of examples of those. And a lot of your homework this week is on op amps. But at the end there, we start to talk about this notion of the Laplace transform in circuits. Now, you guys should know the answer to this already, I hope. But tell me you guys saw Laplace transforms in differential equations, please.
Yes.
Okay, good. All right, that's good. All right, so we're gonna review that and kind of talk about how they apply to circuits a little bit. So we're not going to be as focused on them sort of abstractly for differential equations, but how we use them here. So we've talked about this idea before about circuits being dynamic systems. What does it mean to say that it's a dynamic system? In other words, what's the difference between, say, a dynamic system and a static system? So what would be static versus dynamic? Give me what's the difference, or give me an example at least of what a static system would be.
Just resistances.
Yeah, and so what makes that system with just resistance static? What about that system? So if I just had two R's like this instead of an R and a C, what makes that a static system?
The voltage and current relationships aren't changing, like derivatives or integrals.
Yeah, they're not changing as a function of time, basically. As soon as you turn things on at time t equal to 0, the currents and voltages are all steady. Whereas when I looked at, this RC circuit, we said in general, when I'm looking at something like this, I would have to do KVL around that loop and write a differential equation for it, which for this particular circuit, I would have V of t, so whatever the input is, all right, equal to RC. If I called this the capacitor voltage here, it'd be this, right? And we're not going to go through and solve for how we get to that differential equation. But basically, if I have an input V over here, right? If I'm solving for the capacitor voltage, I would get this relationship right here, and I'd have to solve for what V sub C of t is, all right? So in looking at this here, what I see from it is I would solve this, and the solution has two parts, right? What are the two parts of the solution for this thing? And there's no possible way for me to monitor the chat. So again, don't put stuff in the chat. Just shout out to me. Take your mic off and shout it out.
The transient steady state.
Yeah, the transient and the steady state. So I'd have the steady state piece. All right. And then I'd have the transient. And the transient always consists of a bunch of exponentials. So I'd have an e to the whatever negative t over tau, right? And then if it was a higher order system, there'd be more of those exponentials. And the steady state would be based on whatever the input is. And so you're covering differential equations a little bit more in 2254, but you basically should see there that the steady state answer always kind of is related to, in some way, whatever the input to the system is. If this input voltage over here is a constant, the steady state voltage will be a constant. If that input is a sine wave, then the steady state response will be a sine wave. So for instance, it could be, B cosine omega t plus phi. And we talked about how to do all that stuff, okay? Now, we learned about impedance, which is basically a way of getting away from the differential equation, which applies only to sine waves, and it only applies to steady state voltages and currents. And basically what we did is we learned to say, okay, well, if my input was basically, whoa, what did I do there? My input was, A cosine omega t plus phi. We represented that as a phasor, A angle phi. We then did all of our circuit analysis using impedance. So basically putting in Z sub C is 1 over J omega C. ZL is J omega L, right? And then basically we did all of our results, solved for our currents and voltages, and then brought everything back into the time domain. And we brought everything back into the form of A cosine omega t plus some A, okay? But that only applies to sine waves, and it only deals with the steady state results. And so we learned, about how, and we derived all this stuff for how we deal with it, and basically came up with a relationship that the impedance tells us a relationship for the current. This is an example of a capacitor. So it tells us the relationship between the current and the voltage. It tells us the relationship for the magnitude, and it tells us the relationship for the angles. All right, so we talked through all that stuff. But what happens if we have a different type of input? So we basically said previously, all right, my input is this. V of t is RC dVc dt plus V sub c. All right, so this is our general form. If I had some other input, so let's say today, one of the inputs that I might consider is what if I had, sorry, I'm not sure why I'm, all right, expanding. Let's say I had V of t equal to 5 e to the negative 3t, and I applied it at time t equal to 0. All right, let's say I had that input and I wanted to say, okay, what's the response of that system going to be? All right, could I use impedance to do that? In other words, if this input voltage here was equal to 5 e to the negative 3t applied at t equal to 0, would I be able to find what the steady state result is for that using impedance?
Yes.
Not using impedance, right? Because what was the constraint on impedance?
That it has to be in steady state.
Well, it has to be steady state, but it also has to be a sine wave, right? It only applies if I have a sinusoidal input. And not all inputs are sinusoidal. So we'd like to kind of generalize to say, and get away from the differential equations. So impedance does not work for this because it violates one of the two assumptions. All right. One of the assumptions basically is that the input has to be sinusoidal. Since 5e to the negative 3t is not sinusoidal, we can't use it. All right. So basically, impedance is nice because it gets rid of differential equations. It basically turns everything into an algebraic relationship. And it's great at allowing us to simplify math. We like impedances for that reason. So for a circuit like this, it's not that complicated. But if I had to do some of those circuits that you guys saw really between exam 2 and exam 3, you just imagine doing mesh or nodal with these differential equations, right? It would be a total disaster if you had to do that. You may have thought it was difficult as it was. It would have been even worse if it was something like this. So it's basically, the thing to remember here is there's two shortcomings that are associated with this, all right? The use of impedance. So the shortcomings effectively are the following. Essentially, we are limited to sine waves. That was one limitation. The other limitation is that we cannot do transient analysis, right? Impedance made the implicit assumption that we were looking at transient not included. We implicitly make the assumption that we have sinusoidal inputs and we are only caring about steady state conditions, all right? So the transient's not included. So we'd like to come up with a more general solution that allows us to be able to include more inputs and allow us to look at the transient. And the Laplace transform is a way of doing that, right? So in other words, if I looked at signals like this guy, 5u of t, or this guy, 5e to the negative 3t u of t. Now I've done something here, and I've included something called u of t. And I'm going to ask you guys, you should have seen that with Yahoo by now, but what is this function here, u of t? You guys have seen that with Yahoo, I think. By now you should have seen it.
The unit step.
The unit step, that's right. And so this guy here would basically be something that is 0 for t less than 0, and then it's 1, all right, for t greater than 0. So we would define that as 1 for t greater than 0 and 0 for t less than 0. And so all of the inputs that I'm going to talk about here are inputs that basically we turn on at t equal to 0. That's what that's saying. So if I had a cosine that was, so if the input voltage was v of t, if I had v of t is 5 cosine 20 t u of t, what would that look like if I said, what does this v of t look like here? What would multiplying by u of t do to that function?
Everything to the left of the vertical axis would be 0. Everything to the right would look like a cosine.
Yep, that's right. And that models effectively the power button, right? Basically, we're saying we turn the power button on the function generator or whatever the power system. We turn everything on at time t equal to 0, right? So in other words, it's like there's no input before t equal to 0. It's kind of a mathematical tool for us to use to model the effect of basically starting this circuit up at t equal to 0. All right. And so we use u of t all the time. Okay. Now, what I have here basically is 5 u of t. This is basically thinking of DC circuits. All right. This guy here is classic for what we do with AC circuits. But there's other inputs that we might have, like this guy, an exponential, right? We could have all kinds of different sorts of inputs. I want to be able to handle all of those with something similar to impedance in terms of its easiness of algebra. Okay. So the way to approach that is to use the idea of the Laplace transform. All right. So you guys learned, and we're going to derive a couple of quick Laplace transforms, but you've seen this before. You take the Laplace transform of a function f of t, and you end up with a function of s. All right. So we call this a function of s, which we're going to relate to frequency omega as we go through the next couple of lectures, right? So we start out with differential equations, and we end up with algebraic equations when we do this. We never really end up computing this integral, right? We basically, what we end up doing is we end up applying its results for common signals f of t, all right? So the unit step u of t, all right, well, let's derive its Laplace transform. So looking at the previous slide there, we had that the Laplace transform, we write it with this fancy L, the Laplace transform of u of t. We solve for that using this guy here, so e to the negative st dt. So how do I approach this particular problem? How would I solve that integral? Where would I start? Let's start with this. Let's plug in what u of t is. What's that going to do to this integral if I plug in what u of t is? We said it before, right? We said u of t is a function that is, so u of t is equal to 1 for t greater than or equal to 0, and it's equal to 0 for t less than 0. All right, so help me out with that. How would I do this integral then if that's the case? First of all, I would I'd substitute in u of t, right? So I would substitute in either 0 or 1. So basically, how does that change the integral here?
It makes the lower bound 0.
Makes the lower bound 0. And what do I put in for u of t? I just put in the number 1. Yeah, so it basically becomes the integral of e to the negative st dt. Now that integral, right, ends up being negative 1 over s e to the negative st, right? So you should remember how to do that integral. There's lots of different integrals in the world. Most of them don't matter. E to the negative st is one that's important, all right? And so that's one you probably should know. And because this guy's a definite integral, I got to evaluate it between the boundaries, right? So let's do this. And again, I'm integrating over t. So just to be really clear about this, because there's this variable s going around too. So I say t equal to 0 and t approaching infinity. All right. 1 over s times e to the negative st. As t goes to infinity, what's true about e to the negative st?
Goes to 0.
Goes to 0, right? So I end up with 0 minus 1 over s times e to the negative s 0. So what's e to the 0 always?
1.
1. So that ends up with 1 over s, like that. Okay. So what we say is that for a unit step, we usually have these pairs that we define. We say a function and its Laplace transform. And sometimes we write it like this to say, okay, as we go through the Laplace transform, we end up with its transform 1 over s. Basically, what I was saying here is when I take the Laplace transform of a function, I get a function of s, and we're going to relate that to frequency as we kind of go, right? But you've seen all of this before. Let's do another example here where I have an exponential, okay? Let's think about how that would work. So again, if I say, what's the Laplace transform of, again, we usually write it with the bracket, e to the at u of t, that's negative infinity to infinity, e to the at u of t times e to the negative st dt. All right, now how do I simplify that integral? What's the u of t do to it?
Changes the bounds.
Yeah, it changes the bounds again. So basically I end up with just simply the integral from 0 to infinity of e to the at times e to the negative st dt. So I can combine the two exponentials. How do I combine those two exponentials?
By adding their exponents.
Yeah, you add their exponents. So basically this becomes the integral from 0 to infinity of e to the a minus s t dt, like that. All right, and this becomes what? This becomes, if I do that integral, well, how would that evaluate? Divide e to the anything t. So e to the, I don't know, I'll call it bt. What's the integral of that?
1 over s minus a.
Yeah, this is going to become, it's going to become, yeah, 1 over, I can just write it like this, I guess. Yeah, so e to the negative, or sorry, e to the a minus s t evaluated from 0 to positive infinity, like that. Okay. So that's basically what this guy ends up being. All right. And then if I plug in the two boundaries again, basically what I'm going to end up with is, oops, keep doing that. That's going to end up with essentially 1 over s minus a is going to be the final result if I plug in the boundaries. So again, looking at this guy, what we say is that if I have e to the at u of t, his Laplace transform is basically 1 over s minus a. So the important thing is we go from the time domain to this Laplace domain, we end up with some algebraic function of s. And we're going to show how we use that as we kind of go through here, right? So, all right, the important thing about how we apply this to circuits, you saw this in differential equations. Basically, if I have a function f of t, and it's if f of t is 0 before t greater than or equal to 0, which is sort of the way that we've been doing this, and I said to myself, I want to find its Laplace transform. So in other words, I want to know the Laplace transform of df dt. I plug that into this expression, and if I assume, it's from, so from negative infinity to infinity, and I do df by dt e to the negative st dt. If I go through that analysis, and you can, I'm not going to go through it because it's not that important to us, but basically if you use integration by parts, what you end up finding is that it's s times f of s, all right? So what it basically tells me is if I know, let's say f of t was equal to, e to the negative 4, e to the negative 4t u of t, right? Well, if I looked at the derivative of that function, I would see that it basically would end up having a Laplace transform that would be s times that the transform of that thing. That's not typically how we often apply this. Where you saw this a lot in differential equations would be if you had, let's say you had a differential equation that was 5 equals 3 dx by dt plus x. All right. So you were solving for x. How do I use the Laplace transform to solve in this particular case? What do I do? Well, I take the Laplace transform of everything here, right? So what would that do? How do I use the Laplace transform here to solve this differential equation? What's my next step? How does this help me here? How did you guys learn to approach that in differential equation?
I would take the loss of each and then there's a formula for dx over dt.
Yeah.
Loss transform to that.
But right, so what is the formula? So you take the Laplace transform of each. So if I take a Laplace transform of both sides, what do I end up with here? And I guess I should say, let's say it was a constant, like 5 u of t, like that.
One over s.
Yeah, so it'd be 5 over s because I have that particular thing. What about the other side? What would it be based on what we have right here? I replace so I replace x of t here with its, and I guess maybe to make this totally clear, I say this is their functions of time. So this is x of t plus x of t. So I replaced each of those with their Laplace transforms, right? So what happens to x of t? What do I replace that with? Well, I replace that with x of s. What about the 3 times dx by dt? What do I do with that?
Would it turn into 3s of the integral of xs?
No, it's 3 times x of s, right? So if I take the derivative of a function, right, it becomes s times the Laplace transform, right? So when I take the Laplace transform of it, so you guys use this in differential equations to solve, right? I would write this as 3s plus 1 times x of s. So what you guys did in differential equations is you basically would have ended up with here, you would have written this as 5 over s times 3s plus 1 is equal to x of s. And you would have basically, you would have broken this up using partial fractions. That should be a term that you guys remember you've heard, right? And then what you would do is you basically would take the inverse Laplace transform to figure out what x of t is equal to. All right, that was the approach that you use for differential equations, oftentimes in differential equations. So basically, I take the inverse transform of this. So you guys probably saw, you would have seen that this basically becomes using partial fractions. Let me ask you guys this. How would I approach this with partial fractions before I say too much? How would this get approached? I know you guys saw this in differential equations.
Is it where you have like A over S plus
Yep.
B over 3S plus 1?
Yep, that's totally it. Yeah, plus A over S plus B over 3S plus 1. And you would go through to determine what A and B are, right? And so there's a whole process for doing that. Now we're not gonna deal with partial fractions here. I'm going to assume you guys can do that. All right, but it basically comes down to figuring out what must be the values of A and B so that this turns into that. Okay. All right. And then what you would do is you take the inverse Laplace transform of this thing. So you would end up with what's the inverse Laplace transform of 1 over S? Well, based on what we just did, the Laplace transform of a unit step is 1 over S. So this guy would be A times U of t. This guy here, if I went through the math, would become B times e to the negative 1/3 t. That's basically what I would end up with. Actually, it would become that. B over 3 times e to the negative 1/3 t. And you can go through the process of figuring out what is A and B. All right, I'm not going to talk about that. You have one problem on the homework that has something very similar to this. And it's really just a review of differential equations. I'm not going to talk too much about it, and I'm not going to expect you to do Laplace transform math on the exam. All right, I'm just kind of transiting through this to remind you guys that you did learn about it. All right, so how would I use this for a circuit? Well, in this case, I gave this, I said, well, V of t is equal to 5e to the negative 3t u of t. All right, so what I do is I have a differential equation. We've already talked about this. So if I have V of t, so we're saying that this guy, the input is 5e to the negative 3t u of t. So if you guys had to, you could do KVL around the circuit and get that this is the differential equation, right? Where we say V sub C is the voltage across the capacitor. Oops. V sub C is voltage across the capacitor, like that. All right. If I solved this, basically what I would do is I would convert this into the Laplace domain and say that this becomes V of S, that's the Laplace transform of V of t, equals, what do I do at the other side here? What do I do with the side with the derivatives on it? How do I write that? How do I Laplace transform that?
The constants go out front and the Laplace goes around the derivative of the variable and the variable.
Yeah, it's basically what we showed here is that anytime I have a d by dt, that becomes in the Laplace domain basically just an S. So basically what I end up with here is if I have a derivative, I say it's RC times S times V sub C of S plus V sub C of S, like that. Okay. So in other words, I replace all of the time domain functions with their Laplace transforms. And if I have a derivative, I end up replacing it with S, okay? If I had a second derivative, I would replace it with S squared, right? You guys have definitely seen this, right? So I end up with V of S is equal to S RC plus 1 times V sub C of S. So what we end up doing is, I look at this and I get V of S over SRC plus 1 is equal to V sub C of S. So what I then do is I plug in, well, what is the Laplace transform of this signal 5e to the negative 3t u of t, right? So we had V of S equals SRC plus 1. I'll do it this way. I already rearranged it. V of S over SRC plus 1 is equal to V sub C of S. Okay. So if V of t was 5e to the negative 3t u of t, what is V of S? What's the Laplace transform of that expression? What did we say it was for an exponential?
5 over s minus a,
Yeah.
or in this case, plus 3.
Yep. So it'd be 5 over s plus 3. So basically this guy becomes 5 over src plus 1 times s plus 3. Whatever the inverse Laplace transform of that is the full expressions, the full result, both in the time domain and in the, or both in the transient and in the steady state. And so basically what, if I separate this out, do the partial fractions, I'm going to end up with something that's of the form a over src plus 1 plus b over s plus 3. And I inverse Laplace transform that. So what's the inverse Laplace transform? Without getting into the weeds, what type of function is both of these results?
An exponential.
Both of them are exponentials. That is correct, right? So this guy would basically become a over rc times e to the negative t over rc. This guy would become, and it's times u of t. And this guy would basically become b e to the negative 3t u of t is equal to v sub c of t. Now, which one of those, well, this one is the steady state, the particular, right? This is the steady state. This one here is the transient, the one with the RC in it. All right. So basically this approach allows us to solve for both steady state and transient, and it's cleaner than differential equations, right? It's a lot less work than differential equations typically. And it gives us the transient stuff. And so it turns out we have a way of using and doing circuit analysis by using this approach. And the way we do that, all right, is I take the Laplace transform of both sides of our typical relationships. So there's a differential equation for a capacitor. I of t equals c dv dt. So again, if I was looking at a capacitor, I'm saying here's V, here's I, right? And we define those in the time domain, and it looks like that. So if I take the Laplace transform of both sides of this equation, what do I end up with? Well, I say that the Laplace transform of I of t is simply I of s. And let's just be clear of that. So I of t, we're saying whatever function it is, it has a Laplace transform I of s. And v of t, whatever function it is, it has a Laplace transform v of s. How do I use that information to transform this differential equation into the Laplace domain? How would I write that? You guys take differential equations? Or are you afraid to talk? My experience, this is the main thing they talk about in differential equations. What do I do with that?
You see that's V of S?
Well, dv, so the Laplace transform of v of t is v of s, but what happens to that side that says c dv dt? What do I do with it?
I'm a little confused of what you're asking here, but if we're
Well,
taking Laplace,
what's the Laplace transform of c dv dt? If we know that the Laplace transform of v of t is v of s. I mean, you guys did this probably for weeks on end in differential equations, right?
so in that case, would it be c times v of s?
It would be sc times v of s, right? We replace the derivative, the d by dt, with an s whenever we do that, right?
Don't we also add in initial conditions?
So that is a great point. Don't we typically add in differential equations or initial conditions? You are correct. There is one difference between what I am doing here and what you guys did there, which is to say that I am, and you probably don't remember this, but I have set my limit here to negative infinity. That changes things. The implicit assumption that I am making for all of my, and so I've been making these little points off to the side, but not saying anything about them, is I'm basically assuming that all my initial conditions are 0. But that is a great observation. I'm not including that. Okay. If I did, there's some other term like, I don't know, times f of 0 or something like that, right? It would be something like that that would also be included. But basically, I just end up replacing the d by dt's with s's. All right. What this gives us is effectively an impedance result, very similar to what we had when we looked at the impedance for a circuit. What I have is here that V of S is equal to, if I bring that to the other side, I have 1 over SC times I of S. This is an Ohm's law-like relationship. Now, just to remind ourselves, if I had a capacitor, I would say the capacitor, the phasor on a capacitor, when we did impedance, was V sub C equals 1 over J omega C times I sub C of S. Or sorry, not I sub C, times the phasor I sub C, right? That's what we basically just learned previously. These two expressions here look very similar, right? What would I need to do to make them the same? What has to be true about S to make those the same?
It's J times omega.
Yeah, if S is equal to J omega, that happens in a special case where our inputs are sinusoidal. So what we're going to learn here basically is that for any function, we can use the Laplace transform and basically have this idea of a Laplace impedance. So basically we say that the Laplace impedance of a capacitor is this 1 over SC. And if we have a special input that is in a sine wave, we use S equal to J omega. All right, so we're going to deal a lot with that, but what's going to happen if I look at an inductor? All right, well, we should be able to know, right? If I have an inductor, this is the relationship. So here's V of t, here's I of t going this way, right? So if I Laplace transform this, we say that the Laplace transform of V of t is V of S. We say the Laplace transform of I of t is I of S, okay? So if I look at this here, I get V of S. Again, let me ask you guys. So you tell me how do I apply the Laplace transform to both sides of that equation? V of t equals L di dt. What's that become?
Yeah, the S equals SL IS.
Yep. And again, I'm assuming that there's no initial conditions because they just kind of muck everything up if we include them. All right. And there's some explicit reasons why I'm doing this, but this here is very similar to what we said. If I had sine waves, I would have had VL, the phasor, is equal to J omega L times IL, the phasor, right? So these guys look very similar. And so this leads us to, again, what I'm calling a Laplace impedance. So for the capacitor, it was 1 over SC. For this guy, it's SL. And for a resistor, right, it's just going to turn out to be that I get V of S equal to R times I of S. And we can say this guy has an impedance that's just R again, all right? Now, where do we use this? All right, well, where we use this is it says, all right, if I know that Z capacitor is 1 over SC, and I know that Z resistor is R, what that says is, and we did this before, our differential equation got us to a particular result. So let's say again that I have V of t, this input here. Let's say it's equal to 5e to the negative 3t u of t, okay? Rather than writing out the differential equation by KVL, what I want to do is I want to see if we can take this guy over just like we did with impedance, and move it to the Laplace domain. In other words, take the Laplace transform of this input. So make this 5 over s plus 3, right? Replacing, so in other words, this is V of s. And then put in the impedances of my capacitor and resistor. So call this guy R, call this guy 1 over SC. Okay, I should get for this the exact same result that I would have previously. All right, so what happens here with this result? What does this look like? How would I solve for this using this approach? If you were doing impedance, well, how would you have solved for V sub C of S in this case? Right? Can I say this is a voltage divider?
Yes.
Yeah, right. So I can say if I had a voltage divider, how would I approach this to solve for V sub C?
Vs over R plus 1 over SC time, all of that times 1 over SC.
V of S times 1 over SC divided by R plus 1 over SC. Now what we typically do is we make this a rational function of S. What does that mean, to make this a rational function of S? It uses a ratio of two polynomials. So I multiply top and bottom by SC, like that. If I multiply top and bottom by SC, that's equivalent to multiplying by 1, right? So what happens if I multiply 1 over SC times SC? Well, I get 1, right? So this becomes V of S times 1 over SRC plus 1. Now, this result that I have right here, V of S times this, is the exact same thing I got when I wrote out the differential equation and took the Laplace transform of the differential equation. So it says is that I can basically use the same approach to always write out for myself what the relationship is using just basically the impedance approach. I can get to this kind of generalized approach that I can use for any type of input. All right, now this leads to a thing that we talk about a lot, which is kind of related to what we were doing with op amps. We talk about how we relate inputs and outputs. We talk about this idea of getting a transfer function from a circuit. So what I do is I talk about how I relate the transform, the Laplace transform of an input to the Laplace transform of an output. So if you look at that particular approach here, all right, the way we do this is we say that the transform, this block diagram idea here, the way I use it is I say the transform of the output is always equal to whatever H of S is times the transform of the input. All right, what we do is we take the input here, multiply it by H of S to get the output. All right, transform of input. So we multiply those two together. This thing, H of S, is what we call for ourselves the transfer function of the system. Okay. And we're going to use that term a lot, right? So for this particular circuit, we just found that V sub C of S, we use the impedance to get V sub C of S is equal to V of S times 1 over SRC plus 1. This guy here is the transform of the input. It's the transform of this guy here, the V input. This is the transform of input. This V sub C of S is the transform of the output. It's the thing that I'm solving for, the voltage across the capacitor. And if I want to figure out what V sub C of T is, I take the inverse Laplace transform of that result. This thing here is what I would call the transfer function for the circuit. All right, we're going to talk a lot about this idea of transfer functions. We call this guy a transfer function. It tells us basically how the input transfers to the output. And so that's why we call it a transfer function. And so I would say this guy is H of S equal to 1 over SRC plus 1. But generally, we're going to deal with sort of simpler circuits than you guys did in the last section where you had all kinds of crazy meshes and things. Generally, here we deal with simpler stuff because we're going to keep them typically in kind of functional form rather than kind of focusing on numbers. And there's a reason for that. Okay. All right. So some key takeaways from here, and we're going to, on the lecture on Wednesday that I'll post, we'll look at some examples of this. But basically in what we call the Laplace domain or the S domain, the output is always an algebraic function of the input. Okay. So what we do to get to this, basically we take the Laplace transform of our input voltage or current, determine the transfer function of the circuit using basically this Laplace impedance, all right, that we've determined. Then we take the Laplace transform of the output and then put everything together to figure out what the full output is in the time domain. The nice thing again is that I can avoid writing the differential equations, right? Which is messy, particularly if you've got a more complicated setup. Okay. All right. So that's what we're going to talk about again more on Wednesday, but I'll stop there for now.